Hi, welcome to Mr. Tompkins' physics class. Today we're going to talk about relative motion. Now, we define motion as the change in an object's position when observed from a stationary reference point. The reference point in this case is the key point that we want to look at. It's that main thing that we got to talk about because we're going to start choosing our reference point to be different each time. Here I have some pictures. I want to go ahead and start explaining. Here's this first picture here. This picture right here is a bus. And the bus is traveling down the road. And if I look, I can see that motion is relative to the observer. In this case, whenever I'm sitting on the bus, it seems as though everything on the bus is not moving. But if I look outside the window, well, now it looks like these trees are zooming past me, and they are in motion. So this is showing that, or illustrating this idea that motion is relative to the observer. Now, behind here, we have Galileo. And Galileo was actually excommunicated from the church because of his teachings on motion and relativity. One of his biggest things was that the earth moved. Instead of the earth being stationary and everything moving around the earth, he believed that the earth rotated, and that's the reason why the sun came up and went down. And it rotates roughly around 1,000 miles per hour. Now, the church didn't like this. They said, their argument was that if the earth rotated, how come objects that are stationary on the earth aren't being smashed up against the wall? How come those objects aren't moving while the earth is moving underneath them? Now, Galileo said, duh, any sailor knows that if I want to catch something from the crow's nest, and so here in this ship, I have a crow's nest on this ship. If I want to catch something that's dropped from the crow's nest, I don't stand at the back of the ship. Instead, I have to stand at the bottom of the mast, because whenever that object falls down, it's going to fall down with the mast. He did not actually conduct this experiment. It was just a thought experiment. But it's true. If I want to catch something in a moving vehicle, then I have to stand where it would normally be if that vehicle was stationary. So let's talk about some examples of relative motion. Now, Galileo's example of the moving earth, the earth rotates at 1,000 miles per hour, but us being on the earth, we're not being slammed up against the wall at 1,000 miles per hour. That would be very painful. Instead, because the earth and we and the earth are moving at the same speed, relative to the earth, my velocity is stationary or zero. So I am not actually moving compared to the earth. Now the earth is moving and I am moving, but not differently. Another argument, or here's another example. I have a truck driving down a highway, and then I hit a bug. Now we've all seen a bug inside a car. The bug flies around as though there's nothing going on, that the car is not zooming at 60 miles per hour. Instead, what we see that the bug acts as though the car is stationary. But if the bug is on the outside of the car and it's measuring its motion based on the earth, well, the car now is traveling at 60 miles per hour compared to the bug. And you see what happens to the bug. It gets smashed. Here's a video talking about projectile motion and how it's relative. And we're going to watch this video. It's a couple minutes long. Just watch it and see what the gentlemen have to say.
This steel ball can be held up by the electromagnet. Now I'm going to open the switch and you watch the motion of the ball. The ball is accelerated straight down by gravity along a line parallel to this vertical reference line. As you can see, the electromagnet is mounted on a cart that can move. And I'm going to do exactly the same experiment that Dr. Hume did, but this time while the cart is moving at a constant velocity. The cart is pulled along by a string which is wound around this phonograph turntable, and that pulls it with a constant velocity. When the cart passes this line, the ball is released, as you can see. I'm going to start the cart down at the end of the table so that by the time it gets to this point, I can be sure it's moving with a constant velocity. Now, I want you to watch right here so that you will see the ball falling. I think you can see that the ball landed in exactly the same position that it did before. when Dr. Hume did the experiment with the cart fixed. But this time, the ball could not have fallen straight down. Let me show you why. The ball was released. At that point, if it had fallen straight down, because the cart moves on in the time that it takes to fall, it would have landed back here somewhere. But it didn't. Now I'm going to do the experiment again. And this time, I'm going to let you watch the motion through a slow motion camera, which is fixed here. As the cart moves by, the ball will fall, and you can watch in the slow motion camera. I'll show you this again. This time there'll be a line on the film so that you can see the path. I think that you can see that the path of the ball is a parabola.
Okay, but anyways, whenever the ball was falling, you notice that it followed the path of the rod. It followed it straight down. So relative to the cart, the ball was actually traveling with the cart horizontally. Now, relative to the earth, the ball was undergoing projectile motion. So let's talk about how we can do calculations with this relative velocity. And in order to do this, we need to talk about the art of subscripts. Subscripts have to be arranged in a certain way for this to work. And we will read these subscripts in a manner that will help us. So I'm going to go ahead and grab a pen here and let's talk about it. Now, the velocity of a bug with respect to the windshield. So now we're talking about a bug with respect to the windshield. I'm going to use the art of subscripts and I'm going to put the bug before the windshield. Now, this is important when we start doing our calculations later on because we will need to do this correctly in order to get it right. So whenever I write the velocity of the bug with respect to the windshield, it's going to be the velocity of the bug. Now, this is a vector, so we need to make sure that we keep direction with it, because whenever we start talking about two-dimensional motion, we'll have to do vector addition. Whenever I do my subscripts, I start with the bug. So this is my first one, and then I end with the windshield. So this is going to be my second one. So it's going to be bug, and then windshield. So it's the velocity of the bug with respect to the windshield. Now, whenever I do the velocity of the windshield with respect to the ground, well, it's going to be velocity. But then I start with the windshield, which is W, and I want to talk with respect to the ground. And then the last one that we can talk about is the velocity of the bug with respect to the ground. And it looks like this. Now, it's important that you keep these subscripts straight, okay, because if you don't keep the subscript straight, then the equations are not going to work out properly. Now, one thing that we also need to know is we need to know that, well, the velocity of the bug with respect to the windshield is exactly equal to the negative of the velocity of the windshield with respect to the bug. And so this is going to be the velocity of the ground with respect to the windshield, but it's going to be negative because they're going in opposite directions. So this will be the negative velocity of the ground with respect to the bug. Okay, so if I have the subscripts one way and I need them another way, I can just put the negative sign in front and it changes or it reverses the subscripts. All right, it's going to be important to know for this next topic. So here we go. We're going to talk about a one-dimensional uniform relative motion. Now, the uniform just means that the object is not, sorry about that. Let me see if I can stop that. It just means that the object is not accelerating. Instead, we're going to have a constant velocity. So we're going to go ahead and start this. And here I have a cannon sitting on a cart, and it's going to shoot a ball off with a velocity respected to the cart or relative to the cart of 5 meters per second, and it's in that direction. And so this velocity is with the ball with respect to the cart, and so it's going to get this the variable v subscript ball with respect to the cart. Now the cart's going to be traveling with respect to the earth or the ground with a 5 meters per second in that direction. So in this case, the subscripts are going to look like this: the velocity of the cart with respect to the ground. Now I want to know, well, what is the velocity of the ball? Velocity of the ball with respect to the ground. Now I don't know that yet, but I'm going to show you how to calculate it. Now the technique you want to use is called the subscript sandwich, and I made that up. But we're going to use a sandwich of subscripts to get what we want. In order for us to figure out the velocity of the ball with respect to the ground, then I need to have these both subscripts on the outside. So this is like my bread. And then on the inside, I need to have matching subscripts. So if I look at this, in order to get the velocity of the ball with respect to the ground, I need to add two vectors. All right, and those two vectors are going to be the velocity of one object with respect to another plus the velocity of the other object. Okay, and these are both vectors. Now, the first one I want to look at is that it's the ball. So I need to have the first one be here, be the ball. And then over here on this last one, I want to find it with respect to the ground. So I'm going to put the last subscript of the ground. Now, in order to do this, well, I need to know the velocity of the ball with respect to the cart. Notice how the ball and the cart are here. And so that's going to be, it's going to be the cart. So let's go ahead and erase that. Get my pen back out. Ball, cart. And then over here, I know that the velocity of the cart with respect to the ground. So now if you look at this, I have a sandwich with the ball on the outside and the ground on the outside, and then my carts in the middle. These two in the middle have to agree in order to cancel out. So now if I fill this out, well, the velocity of the ball with the cart, with respect to the cart. So here's the velocity of the ball with respect to the cart, and it's going to the right. So I'm going to leave that positive. So it's going to be 5 meters per second. And I'm going to add to it the velocity of the cart with respect to the ground. Now the velocity of the cart to the ground, well, the cart's going to the left, so I'm going to make sure that that's a negative. And whenever I put it in here, it's going to be a negative 5 meters per second. Okay, don't forget the negative sign. These are vectors, and we need to illustrate the directions. And so if I look at this, well, then the velocity of the ball with respect to the ground should equal 5 minus 5, which is 0 meters per second. And so if I were to take a ball and shoot it out exactly equal to the direction of the cart, the ball should have a 0 horizontal velocity. Is that true? Well, let's see.
Ever drop straight to
Let's go ahead and reset this, and then we'll watch this Mythbusters.
Can an object shot backwards while traveling forwards ever drop straight to the ground? It's a fascinating thought, but trying to prove it is bringing our physics team unraveled. Tori, Carrie, and Grant are struggling to prove the supposedly common sense myth that an object drops straight to the ground when its forward and backward momentum are exactly the same. With the forward and backward momentum matched as close as they're going to get it, the pressure's on Grant for a perfect release.
I don't know about you guys, but that looked pretty good to me. Let's check the high speed.
It really looked good to the naked eye, but the judge in this case is the high speed.
Oh my God, it's like a cartoon. It's just in the air, it stops and it just falls.
Look at that. Fantastic. I mean, look, it doesn't move at all. It's going straight down.
Woo! We did it! We did it! Yeah! Vector edition! Yeah! We canceled out velocity!
After 3 days of suffering, that single shot brings the myth to an end.
I can't be happier. We actually got the speed of the car to match the speed of the soccer ball, and we got a perfect straight down drop.
Ladies and gentlemen, the laws of physics are still hard at work.
Okay, so that just confirmed it. If I were to shoot a ball out the back of a car exactly equal to the car's forward velocity, well, then the ball will drop straight down. I don't recommend it, but if you're trying to exit a moving vehicle, don't jump forward, jump backwards. Now let's look at a two-dimensional idea. So here's the video. We're going to start off with the video first. And this is my favorite time to go driving, and that's driving in the snow, when it's snowing. And so here we go. Let's watch this. Everybody has seen this type of motion before. Okay, it looks like I'm going through a star field. Now, the snow itself looks like it is coming right at me. But we all know that's not true. My car is not a magnet for snow. Even though I have to clean it off in the morning, it's still not a magnet. Now, what I'm seeing is that motion of the snow looking as though it's running right into my car, like it's making a beeline for it. That's not the case. The snow itself is actually falling straight down. So, let's grab an arrow, and the velocity of the snow is down. So that's the velocity of the snow with respect to the ground. Now, the car itself is actually traveling in that direction. Now, it's going to be traveling a lot faster than the snow is. So the velocity of the car with respect to the ground. Now, I want to know, well, what exactly is the velocity of the snow with respect to the car? I want to see if the snow actually is moving towards the car. So if I look at this, I need to set up my equation first. So I need to have the velocity of the snow with respect to the car. So I'm going to start with snow first. So velocity of the snow, and I'm going to do it with respect to the ground. And then I'm going to add to that the velocity of the ground with respect to the car. Now this is where we have to start talking about, well, flipping those subscripts. Because look, I only know the velocity of the car with respect to the ground, and I only know the velocity of the snow with respect to the ground. I don't know the velocity of the ground with respect to the car. I do know that it's going to be the opposite of the velocity of the ground or the car with respect to the ground. So let's say the car is traveling at 36 meters per second, and the snow is falling down at 1 meter per second. Okay, so now I got to do me some math. Now, because these are vectors and they are at 90-degree angles, whenever I add these two vectors together, it's going to look something like this. Following the head to tail method, it's going to be the velocity of the snow. Oh, hold on. I can't do the velocity of the snow with respect to the ground, right? I have to do the velocity of the ground with respect, the velocity of the car with respect, the velocity of the ground with respect to the car. So this one's going to look like this. Here's the velocity of the car, or of the ground, with respect to the car. And then I'm going to have another one that's going to point straight down. And that's the velocity of the snow with respect to the ground. Okay, so the velocity of the snow with respect to the ground we said was 1 meters per second down. Plus, and that's down, the velocity of the ground with respect to the car, which we're going to say is negative 36 meters per second that way. Now, in order to do this, I'm going to have to use the Pythagorean theorem. Because they make a 90-degree triangle, to find my resultant, which is in this case, starts here and goes to there, I needed to use the Pythagorean theorem to find out that length. So I'm going to do the square root of 1 squared plus the square of negative 36. Now I'm going to pull out my calculator here. Let me go ahead and pull up my calculator down here. And I'll pull it up here on the screen so that we all can see. And so I want to do the square root of those two numbers. Now 1 squared is going to be 1, and 36 squared, let me go ahead and load that up. 36 squared equals 1,296. 1,296. And I want to take the square root of that. So I'm going to add 1 to this 1,296. And then I'm going to take the square root. I just got to find the square root button. Oh, right here it is. For some reason, it's not over with the rest of them. And I square root it, and I get that the object is moving at 36. It's not very much bigger, but 36.01 meters per second with respect to the car. So the velocity, this is the velocity of the snow with respect to the car. Now, I also need to figure out this angle. I know that this is going to be 36. The length of this side is 36, and the length of this side is 1. And so the angle, to find the angle, I'm going to use the inverse tangent function, minus 1. And in this case, it's going to be opposite over adjacent. My opposite side is 1 over 36. And that's going to give me my angle theta. So let me pull up a calculator here again. And I want to take 1 and divide it by 36. Hit the equal sign, and that's the number. And then I want to take the inverse tangent. And so inverse tangent, and that gives me that the angle is going to be 1.6 degrees. So theta equals 1.6 degrees. Now, that is that angle right there. So it's not a very big angle, which makes it appear as though the snow is coming right at me. In actuality, the snow is falling straight down. And so those are our two cases of relative motion.